Then we're going to look at radical functions. And what a radical function is, first a radical sign is what a lot of times people call a square root sign. But what we're going to look at in the next couple videos is the fact that sometimes it's not a square root. It could be a cube root or a fourth root or a fifth root and that kind of thing. So, but for now, we can call it square root if you'd like. A radical function would be any function that has x under a radical sign. And what we're going to do here is make a table of values just so you can get a sense of why the graph is shaped like it is. This is going to be much easier than graphing rational functions. What we do here, first, think, what is the square root of 0? I conveniently selected some x values. We're going to see what y values come out of it. Well, the square root of 0 is just 0. What's the square root of 1? The square root of 1 is 1. What's the square root of 4? The square root of 4 is 2. What is the square root of negative 1? Well, you know it's I, but in this case we're going to say DNE does not exist because imaginary numbers do not show up on our typical Cartesian coordinate system. We're just going to graph these 3 points. 0, 0 is the origin. 1, 1 is right here, over 1, up 1, and over 4, up 2. And you see it's not a line, it does have some curvature. And of course it would continue in like manner. I could go on down. I selected these because they're perfect squares. But notice also that it abruptly stops at one point because I can't take the square root of negative numbers. So this is the basic shape, and we could use a graphing utility, it would give us that same shape. But really with square roots, we can just memorize this basic shape and be able to tell the domain and range, then you're in pretty good shape. It's going to be an easier topic than graphing rational functions. So let's look at some specific examples. What if we were asked to graph, say y equals the square root of x minus 2 plus 1. You remember from your basic graph shifts, when you subtract inside the function, it goes to the right. When you add on the outside of the function, it goes up. But what's even easier than memorizing that here is just think if I'm on the inside of the function, I'm going to change the sign. If I'm on the outside of the function, I'm not. So I'm going to write down the 0.21. And we really don't have a name for that point, but it's important that you write that for a couple reasons. One reason is that this point is where this graph is going to start from. 2, 1, right here. Now I know the basic shape. I remember if I go up 1 over 1, it's there. If I go over 4 and up 2, it's there. But you really don't have to count off necessarily. Just get this basic shape in. We're not graphing to perfection here. We just want to understand the basic concepts of the graph. So that's one reason why it's important to write that point, is to give you that starting point. Remember that if I were to venture over here, for example, 1, and try to plug that in there, what happens? Well, 1 minus 2 is negative, and that creates imaginaries which don't show up on the Cartesian coordinate systems. That's the reason it abruptly stops here. It doesn't go this way. Another reason why it's important to write this out is for domain and range purposes. Domain, range. Okay. Remember, domain is all the x's covered by the graph. With rational functions, we could just say the domain was all values except for excluded values. But here, it's going to be all values beginning with 2, because remember, domain is x, and continuing from ever. If I just look up here, this is my x, this is my y, I can see this number is going to be critical when declaring the domain. So I can say my domain here is x greater than or equal to 2. My range, that's all the y values covered, so we go with a 1. It's going to be all y values greater than or equal to 1. 2 or greater, all the x is covered, that's my domain. 1 and greater, that's all my y values covered, as you can see here on the graph. Another thing that we're going to get you used to here is something called interval notation. This is inequality notation. Interval notation, we'll explain the details later. This will be 2 to infinity. Okay, it says it starts at 2 and it goes to infinity. Notice the 2 has a bracket. The bracket means that you can be equal to 2. If it were a parenthesis, you're saying it cannot be equal to 2. Infinity is an idea of going on forever. You can't be equal to it, so we put a parenthesis. The equivalent interval notation for the range here would be 1 to infinity. And this is going to be a work in progress. I know there are a lot of little things at you here, but you're going to see this quite a bit from now going forward. So we need to get used to that interval notation. Here I have y equals 3 times the square root of x plus 2 minus 4. Again, thinking about that critical value, change the sign, don't change the sign. -2, -4. I'm 2 to the left, I'm 4 down. Notice also we have this 3. Now the 3 is not going to move it anywhere as far as the point of origin for the graph, but it is going to stretch it out. It's consistent with what we said earlier with graph transformations. If you multiply by a number larger than 1, it's called a vertical stretch. It tends to pick it up. So instead of going up 1 over 1, in this case, I would actually go up 3 and over 1. Again, you don't necessarily have to memorize counting it off. I just want to show you why it exaggerates it a bit. Where I used to move 1, I'm now moving by 1 times 3, so I have that extra lift. And instead of going over 4 and up 2, I'm now going over 4 and up 2 times 3, and 1 up 6. So I'll be going over 4 and up 6, which would be, counting it off correctly, about right here. So notice how the graph still has the same basic shape, it just got stretched out by the 3. And if you're confused as to exactly how much to stretch it, you can always graph it with a utility. But the big thing is that we understand the shape, the characteristics of the curvature, and it's going one way due to the fact that square roots can only obtain non-negative values. As far as our domain and range, again, we can refer back to this point. Our domain here is going to be all values from -2 to infinity. -2 is the farthest you can go to the left. It goes to the right forever. Similarly, my range is all values from -4 and up. But writing down this coordinate is very helpful in building that -4 and up there for my range. Here we have y equals negative square root of x minus 2. Again, our critical value here is 0, -2. And the reason it's 0 now is what am I adding on inside of here, not what I'm multiplying. The only way you can shift a graph is by adding or subtracting. So what am I adding here? X plus 0 still makes x. It's not 1, it's 0 for x. And remember, if you're on the outside, you do not change your sign. So 0, -2 would be right here. I know the graph starts from that point. Now we have something new. We have a negative out front. If you remember from before, the negative reflects the graph. So it's going to do the same thing here. It's going to reflect it for us. So we're actually going to go in this direction. If you think about it, if I plug a 1 in here now, it's the square root of 1, which is 1, but I'm making that result negative. So it's making the numbers go down instead of up. And if I go down 2 this way, I'm going 4 this way. Okay, so my graph looks the same basic shape, it's just flipped upside down. And that's the influence that the negative have. It shifts graphs upside down. Now what exactly does that do to the domain and range? Well, the domain, despite the fact that it's flipped upside down, the domain still goes from 0 to infinity. So there is no change there. Remember, domain only cares about x values. And flipping it upside down doesn't change its orientation in the x direction. It's still going here to the right. Our range, however, did get changed. Because when I write these things in interval notation, first I'll do this one in inequality notation. This is all values less than -2. Actually less than or equal to -2. That would be the correct way to demonstrate range in inequality notation, because 2 is the very biggest, -2 rather, is the very biggest y value you get, and everything else, every other y value here is going to be below -2. But in interval notation, the way we write it always is the smallest number first and then the bigger number or bigger idea. Well, what's the smallest this thing could be? Well, it could go down forever if you let it. So we actually start this with infinity, and when you're on the left, you say negative infinities. Negative infinities always show up on the left, positive infinities always show up on the right if needed. The highest number goes second. The highest number actually here is 2. So it's negative infinity up to 2 for our range here. This is somewhat rare, and I don't know that I'm going to ask you this in a quiz or test, but just to be thorough, occasionally you do have a negative on the inside of the square root. You may say, wait a minute, I can't take the square root of a negative. Well, you can if it's negative x, because I'm asking what values of x would be possible here. As long as you make your x 0 or negative, it will cancel out with that negative and make the inside a positive number, which is legal. So what happens to my graph and that negative on the inside actually goes in a negative direction, because it's trying to cancel out that negative. So it looks roughly like this. My domain and range, again, I don't know that we're going to put one of these on the quiz necessarily, but it would look this way. It goes left forever, so we start with negative infinity, goes right to 0, and our range starts at 0 and goes up. Despite the fact that the negative's there, it doesn't affect the y orientation of it. So if you ever have a negative on the inside, to compensate for that negative, x has to become negative or 0, and it forces it in the other direction.